Hello everyone. Today we'll start our first chapter or first section in which we'll give you an overview on the thermodynamics that has already been covered in an earlier course. This is just to make sure that we are all on the same page, because the concepts which will be developed in these lectures will be subsequently used. We'll be discussing about an introduction. To give you an introduction of classical thermodynamics. Now the word classical means we are not talking about any molecular interpretation, or we are not connecting the macroscopic properties to the microscopic properties through the statistical thermodynamics. So we will be only considering the macroscopic properties, and will be only discussing the existence of matter as it is, like it's a bulk matter, but we will not bother what are the constituent atoms and molecules, what are the individual atom or molecules properties. So let us first give you an overview, or give you try to recollect what we usually study in thermodynamics. Now whatever I am going to teach in this chapter or in this lecture is very well known to you, but again this is just to remind you of a few basic concepts and some key ideas that we often encounter problems, conceptual problems. So the first thing first, we talk about systems and surroundings in a very abstract way, in the sense that the part of the universe which you are which you are actually working with is we call as system. Basically, we part of the system and we look at the effects in the surrounding. So surrounding is basically the part of the universe which excludes the system, and system and surrounding together form the universe. And then we talk about many different kinds of systems, like open system, closed system, isolated system, and so on. And then we talk about the definition of work and heat. So work and heat are actually forms of energy during a transformation. It is meaningless if we have this statement that suppose 1 gram of ice has this much amount of heat. It doesn't make sense. However, if I say that 1 gram of ice, when it melts into 1 gram of water at say 100 degrees centigrade, at 0 degree centigrade and 1 atmospheric pressure, then this much amount of heat is released, or this much amount of heat when the water freezes is withdrawn. So that can that makes sense because actually heat and work are actually forms of energy during the transformation. There is no such concept that a system has absolute amount of heat or work. Now, of course, the system possesses some internal energy, and the way we define the internal energy is as follows. Before coming to the internal energy, let us first discuss what are basically out of the other properties of work and heat. Work and heat are known as path functions, meaning it will depend on how you transform the system. Like if you remember your introductory thermodynamics lecture, which you'll get in which are all uploaded in the earlier course on YouTube, or you can get this information in any standard physical chemistry textbook, particularly the textbooks which has been recommended to you. Now, we usually suppose we are talking about a pressure volume work or a mechanical work, and suppose we are going from one particular initial pressure and initial volume, let's say P1 V1, to some final volume, let's say P2 and V2. Now the question is how will I do this transformation? So this is an expansion as we have drawn it. So this is an example of an expansion, and in this case I am showing the work done in a PV diagram, because the dimension of pressure times volume is the dimension of energy or work. Now, if we can do it in many different ways. We can do it in a single step. Then we can actually set the opposing pressure equal to P2, and the system basically expands, and then the work done will be nothing but the area under this curve. We have already done it, because the expression for work done or we can write it as a differential expression for work done, is nothing but the negative of external pressure times the change in volume. And for any finite finite value of the work done, it will be nothing but integration of that P external into dV, where actually the volume change within a finite limit. So now the question is, this work done which we are describing here, if I set the external pressure to be equal to P2, then the volume change is nothing but V2 minus V1, and the work done will be just area under this curve. However, if I go to an intermediate pressure first, which is say P prime, which is somewhere say here, and which corresponds to volume, which is say V prime here, then the work done in the first step will be something like the area under this curve, the red shaded zone, and then in the second step it will be the area under this curve. So you see that the work done is very different. So work done is a path function, and that's why the differential we are not actually mathematically exact differential. So it's an inexact differential, and that's why we use a cross sign. Similarly, for heat withdrawn or heat supplied to the surrounding, that also we write it as D cross Q. Now we already discussed in the earlier course, or it is also explained in the textbook, why actually we use a negative sign here. Usually the convention we follow here is the work done on the system is positive and work done by the system is negative. Now you can think that our classic example for work done the system is actually gas which is confined in a cylinder, and one side we have a movable piston which is frictionless and massless, so that it doesn't the movement of the piston does not actually cause any dissipation of energy. Now the question is, if the gas expands, then actually the system is working, but always the weight of the piston or the opposing pressure acts in the downward, because if you think that we have put the piston or we have put the cylinder vertically, then the force acting on the opposing pressure acting on the gas is actually always downward, but the gas is doing work in the other direction because it's expanding. So from that point of view, we took the work done with the expression in the expression for the work done, we usually take a negative sign to make things consistent. Similarly, heat flown into the system from the surrounding is a positive quantity, but if heat is released from the system and goes into the surrounding, that's a negative quantity. So any energy input, either in form of work or heat, if it is flown into the system, it's a positive, and if it is flown out of the system into the surrounding, that we take as a negative, take to be negative. Now then we say that we basically write the statement of the first law of thermodynamics, and we say that for any cyclic process, the work done will be equivalent to the heat withdrawn. Now what is a cyclic process? The cyclic process is that you basically change, you start from a state of the system. Suppose this is an system is just a gas confined in a cylinder, and then its macroscopic properties or the state of the system is completely defined by three parameters: pressure, volume, and temperature. And of course the pressure, volume, and temperature actually has a relation, meaning they're not linearly independent, so you can choose any two parameters as your like variables. Like suppose I have one particular pressure and volume that defines the system, so automatically the temperature will be defined, and that will be followed from a by an usually the gases will follow an equation of state, which we approximate. We can approximate with a ideal gas equation of state, which is not a very good approximation, which is valid only for dilute gases, as well as at at a very low pressure limit, as well as a high temperature limit also. And then we can actually model it slightly better way using van der Waals gas equation. But whatever it is, it's a model, and there is an equation of state corresponding to that model, and the gas more or less may obey that, a real gas more or less may obey that equation of state for certain region of pressure and volume. And then the pressure and volume, if I change and go to a new pressure and volume, then I do a change in the state of the system. And if we do a change in the state of the system in such a way that after the transformation, the system actually comes back to the original change, original pressure, volume, or the original state. So then it is known as a cyclic process. But after the cyclic process, the surroundings may not come back to the initial step. And we discussed it. Suppose if I expand the gas in one step and then again compress it again by one step, and to make sure that we have the same, my final pressure is actually equal to the initial pressure, then we'll see that there will be some imbalance of the work done, and that we discussed that those work done are equivalent to the lifting of masses in the altitude, the lifting of masses in the at different altitude in the surrounding. Now, so it means that the heat withdrawn is basically equivalent to the work done by the system, and again both work and heat are, as I said, that these are called path functions. So the differential work done or differential heat withdrawn are basically inexact differential. So we have to actually use a cross sign here, and we know that for any cyclic process the system will always come back to the original state if the surrounding also comes back to the initial state, which means there was no work or heat exchange involved. So both sides will be 0, but it may be non-zero also, and that non-zero thing is basically the system actually was used during the transformation. Although it came back to the original state, it is kind of like surrounding used the system to convert some amount of work into heat, something like that, or heat into work. Now the question is that conversion, work into heat and heat into work, in a cyclic process, due to conservation of energy, we can write it, but since basically we are saying the work done by the system will be equivalent to the heat withdrawn from the surrounding. Now heat withdrawn from the surrounding is a positive quantity, work done by the system is a negative quantity. So to keep consistency, we are using a negative sign here. So in other words, if I just arrange this equation, we'll get d cross q plus d cross w is equal to 0. Now if we write this d cross q and d cross w, which is addition of two differential, as du, and we see that the cyclic integral of du is 0. Now cyclic integral means actually you started from a particular state of the system and you are actually coming back from the same state. Like in the PV diagram, we can actually show what is a cyclic integral. Suppose this was my original state, P1 and V1, and then I'm just traversing some path, and finally I see that I come back in the same original state. And what we are finding that although d cross q and d cross w, their differential or their cyclic integral, which basically tells that when you come back to the original state, are actually non-zero, or the differentials are actually inexact differential. Their addition, if I take a cyclic integral of that, is 0, which means actually that quantity is independent of path. So whichever path we take, the cyclic integral will always be 0. So that means actually this quantity, that's why I'm writing it as du, not d cross u, because it's an exact differential now, and that we defined as the internal energy or the energy of the system. And then we wrote the first law of the thermodynamics as du is d cross q plus d cross w. Now using this value of d cross w, which we already used, like minus p external into dv, the first law can be rewritten as du is d cross w minus p external, or p opposing, some textbook write it as a p opposing into dv. So this is basically the expression for the first law. Now the only thing which we did not discuss here is that we assume that the work done here is a kind of pressure volume work. We only consider the PV type of work. We can also consider the non-PV type of work, which are important, particularly in subsequent sections, like when you talk about electrochemistry and other things, but it can readily be introduced in the same way. Like this expression is exact. Du is equal to d cross w plus d cross q, and for d cross w we are actually replacing it by minus p external into dv, assuming that only external work is all the work is basically mechanical work, pressure volume work. Otherwise we have to use the original equation and just write it as in terms of pressure volume work and non-pressure volume work, and sometimes we write it as d cross q plus we write it as minus p external into dv, that's the pressure volume work, plus d cross w, which is the non-PV work. So that way also we could have written the first law. And then from the first law, what we further study is that we want to further study this state function which we got from the right away from the statement of the first law, that I have a state function which is u, which is known as internal energy, and we explained why it is called internal energy, and that we can actually write in terms of volume and temperature, and then we can just expand the differential. It's just a chain rule of partial differentiation, and then what you discover is that this du, the total differential of the internal energy, can be written as the partial differential. So this is just straightforward if we just do it, and plus del u del v d dv, and which we can further write it, this should be dt, and then we can further write it as cv dt plus del u del v d dv. Now the Cv is nothing but the heat capacity at constant volume. Similarly, we can also define another thermodynamic quantity which we said named as enthalpy, and which was defined as nothing but U plus PV. And similarly, we can write the H as a function of pressure and temperature, and then we actually wrote the equation for dH, and that was del H del Tp dt plus del H del P T dP. And again, just like we showed that the Cv is basically change in internal energy at constant with respect to temperature at constant volume. Now Cp is nothing but the heat capacity at constant pressure, and dH is nothing but the heat withdrawn at constant pressure. So by definition, Cp is nothing but del H del T and using that notion we got a similar equation. Now then we talked about the second term, which is this term del U del Tv. How do you calculate that? And then we talked about an experiment which was known as Joule's experiment, where we talked about some adiabatic expansion and how Joule actually tried to measure this term, and he found that del U del V T dV is actually 0, and but it is actually will be non-zero for a real gas. So we write it that for ideal gas it is 0. Similarly, by the same token, this should be H. Similarly, by the same token, we can also say that for ideal gas, del H del P T, that term is 0 for ideal gas. But for other gas, there was a fantastic experiment which we discussed, and that is known as Joule-Thomson experiment. And Joule and Thomson did this experiment to figure out what is the value of del H del P T for any gas. And if you remember, final expression for the Joule-Thomson coefficient was something like mu Jt into Cp, where Cp is the heat capacity at constant pressure and mu Jt was known as Joule-Thomson coefficient, which was identical to the temperature drop per unit pressure at constant enthalpy. So that basically gave us an equation to measure the quantity, which is del H del Pt. And next we actually then usually discuss about the properties of H, or the enthalpy, and then we talk about thermochemistry, where we talk about the Hess's law of thermochemistry, and we talk about how the heat change is associated with various reaction, and we can how we can actually talk about the enthalpy change. Basically, enthalpy change will be nothing but the heat change at constant pressure. So most of the chemical reactions are also happen at constant pressure. So that's why enthalpy is a natural quantity to discuss about. And then we talked about the endothermic and exothermic reaction, where an endothermic reaction is defined as when heat is flown into the system. So by definition, for endothermic reaction, delta H is positive for endothermic reaction. And similarly, if heat is produced in the reaction, and that we call as exothermic reaction, and if it is flown into the surrounding, by convention we take the delta H to be negative. And then usually we switch to the second law of thermodynamics, and the connection for the first law and the second law, when we discuss this thing, we again usually all the textbook actually start with some conceptual cycle which was developed for a cyclic process, which was developed to understand the efficiencies of engines, and that is known as Carnot cycle, which was developed by the or which is basically put forward by the French engineer Sadi Carnot. And he basically said, if we have basically two isotherms which are connected by two adiabats, and if we consider a process like a cyclic process where when the isothermal change is happening, some amount of heat is withdrawn, which is QH, at some temperature TH from a hot reservoir, and then when I'm having the isothermal compression, some amount of heat QC is released at temperature Tc. Then Carnot asked this question, what is the efficiency of this engine, and which is basically withdrawing some heat from a hot reservoir, releasing some less amount of heat to the cold reservoir, and basically converting the rest of the heat to the into work. And then there are many again, this is a pressure volume diagram, and these are basically two isotherms and two adiabats. All of you know this thing. And then when in order to understand the work done which is produced in the entire cyclic process, we figured out that not only, just like we did for the first law of thermodynamics, that we figured out that the cyclic integral of this quantity, that d cross q plus d cross w is equal to 0. From the second law, from the Carnot cycle, we figured out that the cyclic integral of this quantity, d cross q reversible by t, is 0. And that quantity we named as ds, where s is nothing but entropy of the system, which was defined as the reversible heat change at the constant temperature. Now this reversibility is very important. If I have some change of state from, suppose the system is undergoing a change in state from state 1 to state 2 along some path. So if the path does not follow a reversible path, then that heat change divided by temperature is not actually ds, but rather we have to always consider a reversible path, an equivalent reversible path, and that heat change which is associated with the reversible path as opposed to the irreversible path, that heat change divided by temperature will be the entropy identical to the entropy of the system. So that's just a definitional thing. And then we talked about the efficiencies of the Carnot engine, and for a reversible Carnot engine, because all these paths which I have drawn in the Carnot diagram is basically each of them are reversible paths, and we told that it is nothing but 1 plus QC by QH. Now when I write QC, it means that when I write when I say suppose 30 calorie of heat is released into the surrounding, then automatically QC will be negative, and so that's why some textbook actually write this expression as 1 minus QC by QH, where the QC inherently doesn't have any sign, it's just the magnitude, and which is also in terms of the temperature we could write it as 1 minus Tc by Th, and since Tc is always less than Th, the efficiency of the Carnot engine will always be less than 1. Or you can think that if I have the hot temperature, reservoir temperature to by infinite, I'll be approaching approaching very close to the unit efficiency of the engine, or the cold reservoir temperature is close to absolute zero temperature. That way also I can reach to the unit efficiency. But in reality, of course, the efficiencies are much lower. This is all for reversible engine. We usually talk about the Carnot theorem also, which says that between two temperature limits, all reversible engines are equally efficient, and the reversible engine actually is more efficient than an irreversible engine. So these are the two theorems which are known as Carnot theorem. And then we ask this question, okay, fine, so ds, or the change in entropy, is basically defined as d cross q reversible by t, but what is the relationship of d cross q by t if it is not an reversible process or any general process? And then we talked about a very interesting thing which is known as Clausius inequality, and which basically says that ds will be greater than or equal to d cross q by t. It will be equal to d cross q by t if the d cross q is d cross q reversible, or the process is reversible. But if it is not, if it is an irreversible process, then ds will be greater than d cross q by t. We already derived the Clausius inequality in that course, and then using that, now we can actually using this fundamental relation, which is again known as Clausius inequality. As you can see that there is an inequality involved here. So using this Clausius inequality, we can actually combine the first law and the second law, and that basically, if you remember, first law was du is d cross q plus d cross w, and here we are writing du is, instead of d cross q, I can write tds if it is equal, if it is a reversible process. So I can write it as du is equal to tds, and for any reversible process, the external pressure, by reversible process again you mean that we make the changes in such a way that the change in pressure always follows the state of the system itself. So P external is always P itself, the pressure of the system. So we write it as du is TdS minus PTV. So that is one of the most fundamental equation in thermodynamics, which is which we get by combining the two laws, combining first and second law of thermodynamics. But this is again true for reversible process, not for irreversible process. And for an irreversible process, you'll always get the heat change will be greater, the heat change by temperature, the ds will be greater than the heat change by temperature. Now from this relation, which is only for the reversible process, then we can actually get many other processes, and there we apart from the enthalpy, which was defined as U plus PV, we can also define many other state functions. For example, the Helmholtz free energy, which was U minus Ts, and also the Gibbs free energy, which is H minus Ts. And then already we have the expression for internal energy, which is already from the first law. And then starting from this fundamental equation, which is du is TdS minus PdV, we can actually derive many other interesting relations. And all these relations actually lead to some interesting relationship between the differentials of the thermodynamic properties. For example, if I take this du and first take the derivative with respect to, say, entropy, so keeping the volume constant, so what I'll have is nothing but del u del s v, that will be T, and minus 0 because dV is 0. I'm considering a constant volume process. And then in the second step, we can we can take a derivative with respect to volume, and then what I'll have is del S del V is nothing but del T del V at constant entropy. And similarly, so in this case it is we can actually write it more explicitly, what is del 2 del S del V. So we first took the derivative with respect to S, keeping V constant, and then in the second step we took the derivative of this quantity with respect to volume, keeping S constant, and that is nothing but del 2 U del V del S. Similarly, we could also use this, starting from this fundamental equation, we could also first take the volume derivative, keeping the temperature constant, and that if I do that, that will give you minus P. And then if I now again do the second derivative, but this time I am taking the entropy derivative as in the later part, and then what I'll get is minus del P del S V. Now these two quantities are basically identical because U is a state function, and by the chain rule of differentiation, it doesn't depend on the order of differentiation for the state function. So basically these two quantities are identical. So what we establish, what we can establish very quickly is basically the differential relationship between very nice relationship. Let me just write it at the bottom. So we can actually get very interesting relationship, something like del T del V S is minus del P del S V, and this is one of the Maxwell's equation which we got from this particular fundamental equation. Similarly, just like we wrote du is TdS minus PdV, we could also get another equation for dH, because we know that H is U plus PV. So I can write dH is du plus PdV plus VdP, but du is already TdS minus PdV, and I have plus PdV plus VdP. So this PdV cancels, so I'll get it's basically TdS plus VdP. And again from this equation, which is dH is TdS plus VdP, which is another important equation, we can actually get another relation, something like del T, it will be T and P, as you can see, del T del P, and in the first case I have to take S, this S to be constant, and then it will be nothing but del V and del S and P constant. So similarly for the other two, like for using Helmholtz free energy and Gibbs free energy, you will also get similar equation. So it will be minus SDT plus VDP and all these things which you already studied, and I'm only writing the differential forms, which the 4 equations which you get. It will be del P del T V is nothing but del S del V, and it will be T PV ST, and then we have del V del T P for the equation for Gibbs free energy. So we'll get minus del S del P T. So all these 4 equations are known as Maxwell's relations, and these are extremely important thermodynamic relations which we often use to derive many interesting thermodynamic properties. Now one thing we always want to keep in mind is that these equations were developed for any general system. Now moment you have, but you in order to actually apply this equation, you sometimes need the equation of state. You start from something and then you first focus on the process, like is it a reversible process or it is an irreversible process. If it is a reversible process, say for example, am I doing it in isothermal way or I am doing it in an adiabatic way. So all these things first come into picture, and then we use the equation of state, how the transformations are happening, and can we approximate if it is a gaseous system, can we approximate it as a ideal gas, or you have to actually consider the deviations or the departures from ideal behavior, or can we actually use the van der Waals equation of state for our model system. So those things will be important. That is number one. Secondly, the conditions has to be applied in the sense that under what condition, as I said, is it adiabatic or is it isothermal, all these things, those things has to be first checked. Then we apply to the specific cases, and then we basically try to solve the problems. And then also 2 more quantities that we particularly often use are defined as the coefficient of thermal expansion and compressibility, that we usually write these 2 equations, these 2 expressions or these 2 physical quantities as alpha and beta. So alpha is defined as the coefficient of thermal expansion. Now thermal expansion means as I increase the temperature, how the volume is changing. So it will be del V del T at constant pressure, and it is per unit volume, because otherwise alpha will depend on volume. So that is the definition of alpha. Similarly, beta is written as defined as the compressibility, and compressibility means how much volume will change if I apply the pressure. So del V at a constant temperature, and then per unit volume change. But del V del P is a negative quantity, because if I apply pressure, any physical any matter will actually shrink, and that's why to keep the alpha beta a positive number, we actually use a negative value in the a minus sign in the definition. And then we from this actually you can calculate what is the difference between the heat capacity Cp minus Cv, which you can get for other there are also other generalized expression, and from that you will get that it will be nothing but alpha square Vt by beta, which also we kind of formulated or we kind of derived. It's a very easy derivation. So you just have to find out first a general relationship between Cp minus Cv. And how do you get it? You already know that the Cp is coming from here, and then the Cv is coming from here. So you can now basically Cv is related to del U del T V dt, and Cp is related to del H del T P dt, and there is a relation between U and H, because we know that H is U plus PV. That you write, and then you calculate what is the Cp minus Cv for those using that relation, and then you basically use these expressions, the definitions of coefficient of thermal expansion. So this is thermal expansion, or better to call it as a coefficient of thermal expansion. Coefficient for thermal expansion, and then this one we call it as a compressibility. Some textbook actually write it or denote it as kappa T instead of beta. So the suffix T is basically at constant temperature, but we will be using the beta notation here only. Now the next thing what we study is basically what are the directionality for a spontaneous process, which is actually an irreversible process. And then we say that all we can say from using the Clausius inequality is that the entropy of the system plus surrounding together, which is the entropy of the universe, will be always greater than 0 for a spontaneous process and will be equal to 0 for a reversible process. Now, reversible processes are mostly, not mostly, they are indeed idealized process. All natural processes are spontaneous in nature and they are actually irreversible. And then we say that this is not an useful relationship. The reason being this equation is for the entropy change for the universe, but what you want is basically entropy change of the system because we want to actually do some measurement on the system and see the effects on the surrounding. So you want some quantity which will be positive or negative, and that quantity, that positive or negative, will give me the directionality of a spontaneous or non-spontaneous process. So then we say that let us actually find some other quantities which on which we can actually say that not for the universe but for the system, if we can actually trace this fundamental requirement that ds universe must be greater than or equal to 0 for a spontaneous or reversible process, then can we actually get a useful relationship which actually is a property of the system itself. And we figured out that yes, there are two quantities, and one is the Helmholtz free energy. If we look at the Helmholtz free energy at constant volume and temperature, if that is less than or equal to 0, the less than 0 means it's a spontaneous process and equal to 0 means it's a reversible process. And similarly, if the changes are happening at constant pressure and temperature, then we can say the Gibbs free energy change is the correct quantity to look at. And for chemists, actually most of the chemical reactions happen at constant pressure and temperature, and that's why this we always talk about the changes in the Gibbs free energy. And we have the transformations are mostly at the constant pressure and temperature, and then we look at the differential as well as finite changes in the Gibbs free energy, and then we want to see whether how much Gibbs free energy is changing, and then we formulate many other requirements or the conditions from this fundamental equation. So just keep in mind that sometimes we say that the dg should be negative. It's not a correct statement. It's actually the dg for the system. So we should write actually this is dg pt for the system, that is negative. And not only that, it's not only the dg of the system, it's taken at constant pressure and temperature. If the process or the change happens at constant volume and temperature, then the Helmholtz free energy is the right thing to look at. So from a quantity which actually is the entropy change, but which has to be applied for the universe, you cannot talk about only the change in entropy of the system or the change in entropy of the surrounding. You have to think about the system and surrounding together, and which is not an useful thing, because then you cannot observe, because you are also part of the universe. You only want to make changes in the system and see the effects in the surrounding. So a better useful quantities are basically Helmholtz free energy and Gibbs free energy. And considering the chemical processes happening mostly at under constant pressure and temperature, the Gibbs free energy is the automatic choice to look at. Now we'll in next lecture we'll see how we can actually focus on the changes in the Gibbs free energy, and then we can talk about many interesting properties or changes in the system, particularly how we can actually formulate the equilibrium constant, and how can actually we can talk about the phase transitions. So those already we covered in the earlier lecture, earlier course on basic thermodynamics. So you can always again go back to and watch the YouTube video lectures, or you can actually refer to the textbooks which have been referred to you. Thank you.